Howdy, my name is Kristen Stubenese,
I'm Blazer Humphreys.
And I'm Stephen Michaud.
and this is our MXET 300 final project. All the basic goals we set out to do for our in our proposal were completed as part of avoiding obstacles, both dynamic and static, by either stopping or diverting in the direction we were going, taking user input from the gamepad controller, and allowing users to choose the degree of assistance that the robot will use. These all came with the addition of a seamless integration of the gamepad input and the LiDAR input together for the final driving path. During our project, we also discovered that the color vision we wanted was not performing reliably and was ultimately cut.
For our code, we split our program into two modes. The first mode is a free-running mode in which the user can toggle on and off an obstacle detection system that the robot will either run into objects or prevent the user from running into objects. The second is an autonomous mode where the robot will actively drive forward and avoid obstacles.
The SCUTTLE begins in free running mode and will run into any obstacles the user tells it to. Pressing X will enable Obstacle Detect Assist, which will prevent the user from running into obstacles, no matter how hard they try to run into that cone. Notice how the SCUTTLE ignores forward joystick input. For the next part of the mainline function, holding down the A button will cause the SCUTTLE to enter autonomous mode, which will drive the SCUTTLE for the user as long as the A button is held down. The user lets go of autonomous mode and is able to take control. As you can see, the SCUTTLE is expertly maneuvering the enclosed track in autonomous mode. This SCUTTLE can even handle dynamic obstacles. Autonomous mode keeps the SCUTTLE from running into the broom as it's placed in its path. The SCUTTLE works in more than just enclosed environments. Here we demonstrate all three modes of running once more. First, free running mode. And now dynamic obstacle assist mode. Notice how the SCUTTLE stops the user from swinging it into the side of the cone. Autonomous mode. Autonomous mode will continue to run until it avoids its final obstacle. Here we will show that with a dynamic obstacle. Now that autonomous mode is exited, the user can turn the SCUTTLE back around and re-enter autonomous mode to return.
Howdy, this is our MXET final project. My name is Abdul.
I'm Jonathan Burgess.
I'm Richie Digert.
I'm Moizuddin Shah.
And we're going to be talking about our metal detecting robot, Gerald.
All right, so the concept for Gerald is that its primary function is to avoid obstacles, both dynamic and static. He moves in a straight direction until he senses an object with the LiDAR, and then he will turn left and right or right away from the wall depending on where it is. The secondary function for him is to detect metal objects in its path with the metal detector, which will light up an LED on the detector, log it in a file, and activate the buzzer.
We can see the robot there move towards the metal object, detect it with the buzzer, then it will detect the obstacle in front of it, turn all the way around, detect the wall, detect the side chairs, just avoiding everything around it while running a random search pattern. Here we can see a little bit more of a dynamic obstacle using the stick to suddenly point it at it and stop it. You can see it avoids everything very well. The reason it's staying in one area is making sure it's scanning most of the area before it leaves it. You can see it slightly, oh, just detected another metal right there. Ideally the metal would not move, so it would not detect it more than once, but since this was a object on the ground, then it can detect it more than once. You can see it progressing slightly, going towards the other areas. Unfortunately, because of the size of the metal detector, if it goes over a metal from the sides, then it doesn't really detect it, as you can see right there. You can see it keeps progressing, and here's another metal detection. It is only programmed to stop 2 seconds above the metal and then keep going, since it is logging the data and telling the user. And this is the node red. From the user's perspective, for monitoring purposes, we can see that it says detect status, no metal found, and the vector and the distance of the nearest object.
Howdy, this is our final project for MXET 300. For this project, we are constructing a personal videographer robot with obstacle avoidance.
For our personal videography device, we tried to incorporate the following functionality. The base of the robot needed to be able to continue to move away from the subject to keep them in range, while not running into any obstacles, as well as avoiding uneven terrain. We accomplished these by using the TI-M56 LiDAR to return the farthest object and travel towards it, while turning the robot away from the closest detected object. The camera processes frames and uses an HSV filter to identify the subject, along with an additional distance sensor to keep the robot at a certain distance from the subject. Finally, a third ultrasonic sensor was added pointed at the ground to check for those uneven surfaces that are unnavigatable by the scuttle.
The following figures show the final physical model.
The gimbal and color tracking module allows for the red subject to stay in frame. In this case, because Luke is wearing a red shirt, the webcam continuously rotates with the help of a servo motor to keep him in frame. And since the subject goes past the allowable range of degrees, the servo automatically rotates back to its 9-degree origin. A Node-RED GUI and MJPG streamer was used to select our HSV color mask for red subjects. Another Node-RED GUI was used to see the rotation of the servo in degrees. This here shows how the TF Luna LiDAR is used for distance control. The scuttle stops when the subject is too far or too close, and only continues to drive when the subject is in perfect distance from the robot. You can see in the top right and left corners of the GUI that when the person is in proper distance, then the scuttle proceeds to drive. And when the person isn't within the proper distance, then the scuttle stops. This shows how the ultrasonic sensor is used to prevent it from falling off the ledge. You can see in the top right and left corners of the GUI that when the ultrasonic sensor detects a drop, it stops the scuttle from driving. The following clips demonstrate how the robot is able to avoid obstacles dynamically while keeping the subject in the frame of the camera and at a certain distance from the overall platform. The camera here is a GoPro mounted on top of the gimbal. This GUI shows what the scuttle decides to do based on the distance and angle of the nearest object and distance of the farthest object detected. Here the scuttle decides to go left because the farthest object detected is to the left. In other words, going to the left is the best possible course of action as there aren't any immediate and near objects detected that would need to be avoided.
Howdy, this is Team 10. Our project was the fire extinguishing scuttle. My name is Dean Visera.
I'm Carlos Espinal.
And I'm Kyle Grossman.
So the mission statement that we had was our goal was to be able to detect the location of and perform the necessary operation to dispose of any nearby fires within a given room. And to that end, we used multiple specialty IR sensors that were designed to detect fires specifically. We used a BeagleBone Blue for motion control and a LiDAR for obstacle avoidance, as well as the provided actuators to actually dispense the foam.
Here we have all the components that we modeled and 3D printed for the scuttle.
So here we have our demonstration video, which we'll play now.
Howdy, this is our MXET 300 final project. This is the firefighting scuttle. So you'll see that it starts driving around in a linear fashion. And also the LiDAR prevents collisions with any potential objects. In this instance, myself. I'm gonna go this way too, just to prove. For the firefighting aspect, we have 4 IR sensors. And if this lighter will work. Nope, triggered. Triggered? Yeah. Triggered. Alright. Okay. So you'll see when one of the side IR sensors detects it, it spins in a circle until the IR sensor mounted facing the front.
And in a real fire, since one of the side sensors triggered it, if it turned a 360, then the IR sensor that's supposed to trigger the actual fire suppressant would also trigger. And so that's why we make it spin until it actually does trigger. And at this point, since the fire suppressant IR triggered, it stopped. And at this point, it would actually trigger the fire spray. But since the motor is not strong enough to actually press on the button on the fire spray, we couldn't demo it live.
So this is what would happen if it had triggered. So you see here that the motor fired. Is it gonna go backward? Yeah, there we go. Yeah, so you can see it here. It goes forward to actuate it, and then when it loses connection, it turns off. So again.
Show the sensor too.
Yeah, the sensor's there. Sensor's there. Yeah, here we go. Triggers, holds the can down, turns off. Triggers, keeps spraying, turns off. We're gonna demo what would have actually happened if this motor was strong enough. You'll notice here we have a bottom cutout which can show the cam mechanism actuate with the cap right there. So if it had properly worked, it would have shot like so.
Howdy, and welcome to the Auto Follow Luggage. My name is Omar Salazar. The other team members include Noah Anderson, Matt Kleinschmidt, and Alexis Hinojosa. Our project was to create the Auto Follow Luggage, which would autonomously follow its owner. The owner would wear a brightly colored indicator, in this case a neon strap, that would become the target for the luggage to follow. The luggage would also be able to have the capabilities to avoid any obstacles that may come in the way between it and its owner.
Robot's obstacle avoidance consists of detecting these red solo cups and pretty much running the inverse of the color tracking function such that it turns away from the target when it detects it. There are some errors in the actual tracking process that result in it stalling occasionally. But we've gotten this function to work relatively reliably, such that when there are no cups in the way of the robot, it's able to move, but when it encounters a cup, it turns away from it. The tracking of the band is supposed to be pretty much just about the normal color track program, but as you can see, for some reason, the robot just stops and doesn't send any commands to the motor, even when it's detecting the band. We've checked the streamer and the mask values seem to be appropriate, and there are no other targets being picked up, but the scuttle just refuses to move. And in the terminal as well, it shows X values being displayed for the target and motor duty cycles, but the motors don't move. So we're not sure why this is happening. This could be something in the program or just something on the board or something beyond what we've covered in the scope of this class. But this is the point that we were able to make it to with our robot.
Hi, my name's Kaz.
I'm Jordan Deshawn.
I'm Gabriel DeLeon.
I'm Steven Mediterraneo. For our project, we created a balloon seeker and destroyer. Our goal for this was to have the scuttle use the USB camera to identify blue balloons, search them out, and pop them.
Number 2 is long. I think 3 and 2 took the longest amount of time for me. 3 is so open-ended. 350 all day. Seat. Turn. Yeah. Now come get it. Now come get it. Keep going. You got it. Yeah. Hey. Ooh. Should be able to see them. But just in case. Go get the next one. This one right here. Come on, let's go get it. Come on. Let's go get it. It's right here. Come that way. Here you go. No. Get addressed. Okay, it should be within ramming speed now. Ow. That is uncomfortable. the last one. Come on. Let it enter ramming sequence. Better yet, put this right above Mr. Blonde so the camera can see it. Oh shit. Oh, that wall wasn't there before. You didn't see the original dynamic. No.
So the main part was like this, and this was.
Let it run into the balloon now.
But then it flat. Yeah, which is why I had this. This is the reason why.
It's gonna boop the balloon while it's seeing. It's fine. Boop it into a better position.
Very fickle.
Howdy, I'm Alfredo Maldonado here with Shelby Sabo, Koi Tang, Zachary Bollinger, and we're here to present our MXET 300 final project, the Maze Bot, the dynamic maze solving robot. So our project for this class was to have a robot avoid dynamic obstacles on top of being able to perform some other kind of task that our team chooses. So we chose as our secondary task to be a maze solving robot. So the robot would be able to solve any maze you would put it in using an algorithm known as the right-hand rule, where the robot would follow the right-hand wall of a maze, which would eventually lead it to the exit of the maze. Here is a demo of our robot solving a maze while avoiding the walls and dynamic objects. All right, well, that is our project presentation. Thank you very much for listening.
Hello, this is Rico, the project manager and integration engineer. Our final project is called Miss Butler. I'm obviously Rico. My members consisted of Jung Song, Jose, and Taylor.
The objective of our project consisted of creating a beverage serving robot, which we named Miss Butler, and the goal for our project was to include this robot in restaurants to help facilitate the service. Miss Butler would use the LiDAR sensors in order to detect obstacles in front of it, either dynamic or static, and it would also have a scissor platform which would be transporting cup. The cup and the platform would elevate when it reached the target location, and then it would lower whenever it delivered the drink. The scissor lift was 3D printed, and so was the cup holder.
Here you can see that the final model changed a little from our initial design. We added additional height with some extra beams to the back of the scuttle that the scissor lift attaches to. We made this change so that a 3D printed lift didn't have to be as tall to get the drink to reach the customer. Here we have the 3D model of the scissor lift. The way it worked was that a motor was connected to a screw in the middle of the lift. When the screw was spun, it pushed and pulled the beams, which in turn was able to raise and lower the lift. It also has a spot in the cup holder where the sensor was screwed onto.
You can go, yeah.
Hi, this is Team 12 with our MXET 300 final project of the Nerf Bot. Our team consisted of myself, Jessica Bousquet, as well as Tyler Mellering, Carlos Nagel, and Carter Yarbrough.
The goal of the project is to reinforce our understanding of the concepts covered during the semester in lab. The project consists of the creation of an autonomous robot using the SCUTTLE platform that can perform dynamic obstacle avoidance, as well as autonomous shooting of targets along a course.
Hello, this is our MXET 300 project. I'm Peyton Blakely.
I'm Tristan Massa.
And our other team members are Han Hao and Monica Martinez.
Our project mission is basically just design a robot that can deliver a drink to a target while also just avoiding obstacles. But overall, we want to focus on just avoiding obstacles as that is the primary reason for this project. For the actual design built, we use SolidWorks to design these components.
Can you put your hands like in there so I can like you can see the clicking?
Hi there, my name is Keith Swanson, and this is our MXET 300 final project presentation.
I'm Akil Alonso.
I'm Eric Escobar.
And I'm Eric Rocher.
Okay, so our selected mission was to create an autonomous scuttle robot, which uses camera detection to detect obstacles and targets. And when a target is detected, it will engage it using an airsoft gun. Okay, so right here we're watching a sped up clip of the obstacle avoidance code running. As you can see, it's successfully avoiding the obstacles that are present. Unfortunately, it's also detecting some erroneous obstacles. That is due to the HSV filter not having a wide enough band, and the fact that the floor and the lighting is irregular in some places. As you can see, it also detects and avoids moving obstacles. In this clip, there's also some false obstacle detection, but that is mostly because of the irregularities in the floor, such as those brown lines. At this point, we've added the double checking system, so it is more accurate in detecting obstacles. And right there, we can see that it successfully engaged that blue paper target. So right here, we've moved the robot over to the other side of the floor. It seemed to run a little more consistently with less markings on the ground. Right there, it engaged the target off the screen, and it turned away to continue in a different direction. Again, there's a target right there. Okay, and right here we can see that it kind of gets stuck on some pellets on the grounds. So I just pushed it out of the way a little bit. Also in the background, you may hear a little bit of laughing. That's because the airsoft gun isn't launching the pellets correctly. When the airsoft gun was reassembled from adding the relay, there's clearly an error with that reassembly. But as you can see, it works.
Get a good video of the tracking. So the robot will adjust to keep the human target in frame. And then once the machine is armed, it will fire at will at the target.
That hit me. So the red means that it's armed, and so we can look down and it's not shooting anyone. If you look, it follows me, but as long as I stay out of range, it doesn't shoot, and then it gets on target, and it shoots me.
This is Team 15 in our delivery scuttle. This is going to be presented by Stephanis Kamala Noor, Lauren Kerno, Long Vu, and Cristobal Cabrera. In the next slide, we'll see the objective of our delivery scuttle is to transverse from the kitchen door where groceries are placed into the kitchen next to the fridge. While along its path, the scuttle will avoid static and dynamic obstacles along the way.